All right, welcome to our lecture on special purpose diodes. Make sure I'm right in the center of the image right there. All right, so a Zener diode, its main job, I'm going to break this down real basic first and we'll build on it. So imagine the Zener diode like a special guard at the entrance of a water pipe. And its job is to keep the water or electricity flowing through that pipe at the same speed or voltage, no matter if people try to change the amount of water, again, related to electricity going in or out. Like the superhero that keeps everything stable. There's a property called reverse breakdown region. So a Zener diode is built to work in a special condition called the reverse breakdown. And so in simple words, when the water or the electricity tries to flow the wrong way, the Zener diode kicks in and controls the speed, and it makes sure that it stays at the right level. There's a thin depletion region when we're talking about Zener diodes. So all of this should be sort of a recall to just a regular diode. None of these should be new terms. But the Zener diode, it's made in a special way with a very small area called that depletion region where the water, in our case, is analogous to electricity, can pass through. So this area is made super small on purpose so the diode can do this particular job well. So we have two parts of the breakdown. The first part is called avalanche breakdown, same as when we talked about any regular diode. Imagine you get this big rush of water coming in really fast. And this happens when there's a lot of electricity trying to pass through. So in this case, the diode can still handle it, but it's like just a big challenge for it. We have Zener breakdown, and this happens when that water or electricity isn't rushing as fast, but still in the reverse direction. So with the Zener diode, it steps in quickly. It controls the flow, even when it's not too strong. So this is kind of a basic breakdown of what a Zener diode is and what it does. We're going to get in more detail in the next few slides. Okay, so let's go ahead and step up that explanation a little bit. So the basic function of the Zener diode, its main job is to keep voltage steady, even if electric current or the load, the device that is supplying electricity to changes. So it's like a device that makes sure the electricity or again, back to pressure or voltage, that potential difference stays the same no matter what happens to the circuit. A little bit of a step up for an explanation on the reverse breakdown region. Again, the Zener diode is designed to work when the electricity tries to flow in the reverse. Normally, electricity flows in one direction, but when it tries to go backward, the Zener diode helps control the voltage by allowing a steady flow when the direction is reversed. That's what makes this a special purpose diode. And this special situation is called reverse breakdown region. What makes the Zener diode special? Right, stepping up the explanation just a little bit. It's heavily doped, but with a very thin depletion region. So the Zener diode is made by adding a lot of extra particles, the doping that we talked about when we made regular diodes, to the material inside. This is what makes it better at controlling the voltage. It also has a very thin depletion region, which is the part of the diode that controls the flow of electricity, the direction of the electricity. So it's because of this thin layer that makes the diode act quickly to keep that voltage steady. We have two types of breakdown in a Zener diode. Again, this is the step up explanation from the very beginning. Hopefully this builds and helps you understand this. The first one we said was what? Avalanche breakdown. And a step up explanation would be uh, within the avalanche breakdown, this happens when the reverse voltage is really high. So again, going back a little bit to the last explanation, imagine water trying to break through a dam, right? If it gets too strong, the dam, or in this case, the diode, will let the water pass, but in a controlled way. So this can happen in both a regular Zener diode um, at high voltages, right? And then there was the other thing we talked about, which was the Zener breakdown. And this occurs in the Zener diode when the when the voltage is reversed, right? When it's in reverse bias, but when the reverse voltage is lower and the diode starts conducting. What this does, it allows electricity to flow. And what this does, it just keeps that voltage steady. So it happens specifically in Zener diodes. And what does it do? What helps them do their job at those low voltages? So if we were to summarize this, a Zener diode helps maintain stable voltage, especially when things try to change the flow of electricity. And it does this, again, in two main ways, handling high voltages, which is the avalanche breakdown, and low voltages, which is the Zener breakdown. I hope I hit record. Yes, okay, I hit record. Alrighty. Okay, so in this figure, we see a Zener diode, and notice that it is in the reverse bias configuration, where you have the cathode up and the anode in the bottom. Right, the anode is connected to the lower reference, the negative reference of the battery, and the cathodes to the positive reference of the battery. So this is the way you would actually configure it in a circuit. There's a resistor there, and then you have your 12 volt source. Now this particular Zener diode is rated for, it says there in the multimeter 3.545. It's about a 3.6 volt voltage Zener diode. So we'll look at the spec sheets in a little while, but it's going to be close to 3.6, something like that. And so this is just a basic configuration of how you would actually put a Zener diode in a circuit, right? So it says it maintains a constant output voltage even when the current flowing through it changes, and the remainder of the voltage gets dropped across the resistor. All right, so let's look at the importance of understanding electrical characteristics, in this case of a Zener diode, but it's really important for y'all to be able to read a lot of different types of spec sheets, but we'll go through this one together. So we see here that it lists the Zener voltage, or V sub Z, at some Zener current, I sub Z. So what is it? The Zener voltage is the specific voltage that the diode is designed to maintain. So when you have a certain amount of current flowing through it. And why is this important when you're looking at these sheets? So the whole purpose of a Zener diode is to regulate voltage. So VZ, V sub Z tells us the exact voltage level it can hold steady. So for example, if the VZ is 5 volts, the Zener diode will keep the voltage at 5 volts, no matter what happens to the rest of the circuit, as long as you have enough current flowing through it. The next column there talks about the test current, I sub Z, which we mentioned in the first column, right? Because it's V sub Z at some I sub Z. So what is the test current, I sub Z? The test current is the current at which the Zener diode was tested to confirm its Zener diode voltage. So again, you all may end up working for a parts manufacturer of these types of things, and this will become super relevant. It's still very relevant for design, but if you're designing, you'll just end up getting the spec sheet and looking at the properties of the Zener diode, as where if you're manufacturing, you're going to be testing these and making sure they operate at the whatever the spec sheet is. So you'll be filling out the spec sheets, right? So yeah, IZ, the current at which the Zener diode is tested to confirm that Zener voltage. And why is that important? It ensures that the diode works as expected. So imagine yourself either the manufacturer of the component or the user of the component. It shows that at this specific current level, the diode will maintain that correct voltage. So if the current is too low or it's too high, the Zener voltage might not stay steady. So think of this current as that sweet spot for the Zener diode's operation. And you'll design your circuit around the sweet spot. So whenever you're thinking about how do I design something, what are my specs, where do I get them, the components in most cases will uh, limit your or put limits on your design and something that you can work on to make sure those components work properly. And so we kind of work for the components in a way. The next column is the maximum Zener impedance, or Z sub Z. And what is the maximum Zener impedance, or what is Zener impedance, right? So it's the resistance, or it's like the resistance inside the Zener diode when it's working to regulate voltage. So the maximum Zener impedance, this refers to that highest resistance that the diode can show while still working correctly. So all of these are when it's working in its normal state or its stable state, um, before you get to a point where you physically damage the component. And this is important because impedance means that the Zener diode can respond quickly to changes uh, in voltage and regulate it effectively. Or let me clarify that. Low impedance means that with a diode. So if the impedance is too high, the diode might not be able to keep the voltage steady, especially if the current fluctuates. So a lower maximum impedance is better for precise voltage regulation. And the last column here is the leakage current. I can't even, yeah, I sub R and at some V sub R, right? And it's in microamps. So leakage current is, again, everything leaks. Nothing is completely 100% a closed system. So when we're talking about leakage current, it's that small amount of current that can pass through the Zener diode when it's not actively regulating voltage. Now, remember, theoretically, we would say like there's no current, it's blocking all current, so it's not operating. But the reality is it does operate. Some current does go through, and you will have some voltage drop across the associated resistor in the circuit, as well as the voltage dropped across the diode itself. So when the voltage is below the Zener breakdown voltage, it just means that you'll still get some leakage current. You can't say that nothing doesn't get through. Right? So you have to deal with that. And that can lead to things like inherent error in devices, things that you just have to work around in your design. It's going to exist there, and you have to deal with it, right? So your circuit has to be able to deal with it. So why is this important? Okay, we talked about ideally that Zener diode shouldn't allow any current to go through, and we do that on paper, and we do that in the textbooks, the theoretical, and then we get into the practical, right? And so practically or in reality, there is a tiny bit that goes through, and if that leakage current ends up being too high, it could affect the circuit when the diode isn't supposed to be doing anything. So a low leakage current just ensures that the diode doesn't interfere with the rest of the circuit when it's not in use. Right? There's also something that's related to leakage current, which is a safety factor for devices. So it's not just that leakage current goes through the circuit when it's not supposed to and interferes with the operation of the circuit slightly, but it also increased the leakage current that's being generated through capacitive effects from the circuit board to the casings of devices, and it also helps add to that potential hazard, right? Because leakage current is a hazard for people. Um, and that's pretty much it. Why is it important to look at these data sheets? Knowing what Zener voltage is of your component. That's the main job of the Zener voltage. That's going to let you know what voltage you're trying to regulate. So I'll tell you what voltage your device needs to be, your circuit needs to be, handling. The test current, that just ensured that the diode maintains voltage under what typical operating conditions would be. The maximum impedance, this tells how the Zener diode affects its operation, how well it can do its job, right? So lower impedance just means better regulation, higher impedance means not so good regulation. And then leakage current, that just talks about how much current is leaked in that non-ideal state when the diode is not supposed to be working. All right. Okay, I'm gonna have to move up just a little bit to see and I try to keep myself in the center of the camera right there. I try to see the PowerPoint. Okay, so you have four circuits and four different scenarios. The one to the far left, where you see the multimeter is reading 552 millivolts, where the diode is actually forward biased. Now remember, Zener diodes work in the reverse bias region, so they have to be flipped the other way. But in this case, it's configured the way you would any rectifier diode, and so it's not going to operate the way it's supposed to in this direction. So I have a 10-volt source, and I'm reading 5.52 millivolts being dropped across a diode, and the rest of it's going to be dropped across that resistor. That's what's when it forward. That's when it's forward bias. So forward bias is not the way a Zener diode is supposed to work. So that's like the we don't care about that one. Move it out of the way. But now let's look at it when it's configured the right way, when it's in reverse bias in the next three pictures. All right, so the first one is reverse bias Zener diode. So the diode is actually configured properly there in the right direction. You got a 10-volt source. So this is saying that you have the diode in the correct configuration. You have a voltage, 10 volts in this case, which is more than enough to provide current to get the diode to operate in that reverse depletion region. So you're going to drop, and it's going to try to maintain the voltage that it's designed to maintain, which in this case should be, it says down there, the 1N4729A has a 3.6 voltage regulation according to the spec sheet. So what do we have there? We have 3.539. So that second graph looks good, right? The next one, the third one from the left, reverse bias Zener having source voltage greater than VZ. So is the first one. But the second one, they just increased it from 10 to 20. And we get the same thing, about the same thing, 3.563 volts. So we're still getting something that's close to 3.6. It should kind of plateau when you do this. When you get past that Zener voltage, it'll try to maintain whatever that Zener voltage is. Also making sure that it's reverse biased. But now look at the last picture. It is reverse biased, but in this case, the voltage is below the Zener voltage, right? The Zener voltage is 3.6. So whatever the source voltage is, you're going to get that pretty much on the output of the diode because you're not regulating any voltage. So if you have 1 volt, you'll read about 1 volt in the diode, 1.2, 1.2. In other words, all the way till you get up to, past 3.6. You need a little bit higher, something higher than 3.6. And then it starts regulating that 3.6 voltage once you get past that. Then it just plateaus and you maintain a constant, steady 3.6. And I'm recording? Yes, I'm recording. All right, hopefully I can see the slide well enough here. So let's talk about reverse biasing, right? Diodes always operate, these diodes always operate in reverse bias. A regular diode doesn't. So our diode usually works by allowing electricity to flow in one direction, like a one-way street. So when a diode is in reverse bias, it means that the electricity is trying to flow the wrong way, but the diode is stopping it. So this is how certain diodes like this one here operate. They're designed to operate in this reverse bias region, and so they work when electricity is actually pushing the wrong way. Here we have that, so I'm getting messages popping up here. You have a voltage-controlled capacitor here. So this is used in tuning circuits. And what that is, it's a capacitor, right? And remember, the capacitor is like a tiny battery that stores energy for some short time. So a voltage-controlled capacitor is a special type of diode because you can change how much energy it stores by adjusting the voltage. So the amount of, in this case, let's say the electric pressure, if we're equating it to the water. I keep getting a lot of messages. Yeah, so thinking of pressure as that voltage, right? Parallel to that voltage. So these are, again, where they're used in tuning circuits, like in radios, where adjusting the voltage can help tune like into different stations. So just like how you dial the right radio station, or in your all's cases when you push the button and that happens electronically for you. All right. So what about the depletion region in this case? So the depletion region as a capacitor dielectric, right? Because of non-conductivity inside this diode, there's a part called the depletion region, just like the other ones. It doesn't let electricity pass through very easily. It acts like an insulator. So the same thing, it's very important in this particular application because it acts like that middle layer of the capacitor. And again, the middle layer of the capacitor being called the dielectric material. It helps store energy without letting electricity flow through it. And this makes the diode act like a capacitor, right? So as the reverse voltage increases, the depletion region widens and increases the plate separation. If you remember going back to the lectures on capacitance, how you calculate capacitance, the distance between the plates is actually, what's that, inversely proportional? No, it's directly proportional to the capacitance. So this is what we're doing here. So when reverse voltage, again, pushing electricity the wrong way, when that gets stronger, the depletion region inside the diode grows wider. So wider, it grows larger. Wider, grows wider. Yeah, wider is probably a better word. Growing. So it's like stretching a rubber band, and in the capacitor's case, it's similar to increasing that distance between the plates. The area where the energy is stored. So the bigger the distance means the capacitor can store more energy. Um, what did you say? The depletion region narrowing? What happens there? Great question. So the depletion region narrows as the reverse voltage decreases. Fantastic question. I know somebody was thinking it. Uh, so just like, not just like before, uh, counter to what we said before, give me 1 second. I hate when the lights go off. There it goes. Alrighty. Yeah, so kind of counter to what was said prior, when the reverse voltage goes down, the depletion region becomes smaller. So, like when you release a stretch rubber band, right? So, if we bring this to the analogy of the capacitor, the plates move closer together, meaning it stores less energy. So, if we were to summarize this whole thing here, the diode acts like a capacitor whose energy storage changes based on how much reverse voltage you apply to it. And again, this becomes very useful for tuning circuits where adjusting the voltage helps control things like radio signals. And it does a very good job of maintaining uh, that constant level of depletion region, which is the capacitance that it's maintaining. Hopefully that made sense. All right, light emitting diodes. You see these all the time, so you're not unfamiliar with light emitting diodes, but let's talk about how they work. What are they, right? So LED just stands for light emitting diode, and it's a special type of diode that emits light, right? So it lights up when electricity flows through it in a certain direction. So it's used in things like, believe it or not, TV screens, traffic lights nowadays, flashlights. You'll see LEDs everywhere nowadays. Uh, when a diode is forward biased, remember the electrons cross that p-n junction and then they recombine. So when you send electricity through an LED in the right way, being forward biased, it allows tiny particles, the electrons, to cross through the LED. So the point where these electrons cross, we call that the what? The p-n junction, correct. And when they reach the other side, they meet with the, right? So an electron has to occupy something. It occupies a hole, right? Hole. Those are the empty spots where the electrons fit, right? So you have electrons and holes. So when an electron and a hole meet, it's called recombination. Just a little bit of a review here, or maybe, yeah, a little bit of a review from before. So what's the question? Free electrons in the conduction band? Great question. So I can relate that too. So what about free electrons in the conduction band, right? So we know that they have more energy than the holes in the valence band, right? So electrons in the conduction band, remember that's the part where they can move around and carry the energy. They have more energy than the holes in the valence band. So the part, again, where the electrons usually stay, where they sit, where they chill and watch Netflix. So electrons move to fill the holes, they lose that energy, and this lost energy has to go somewhere. So really good question on how this relates to free electrons in the conduction band. Any other questions? All right, I'm just being telepathic here and assuming you're asking these questions. The energy between the electrons and the holes, what does that correspond to? Well, that corresponds to the energy of visible light. Fantastic question, right? So we have those holes and energy and electrons swapping places or occupying places. What does that mean, right? That difference in energy is actually, it correlates to the visible light. So the energy difference between the electrons and the holes is just the right amount to create visible light, photons, right? So the light we can see with our eyes. So this is why LEDs um, give off uh, light when they move around, when the electrons move around inside them. Any other questions? Recombination. What happens during recombination? Oh, yeah. So, like I mentioned before, during recombination, electrons release their energy, and they release the energy into something called photons. Um, Great question. So, um, electrons recombine with holes, right? They release that extra energy they had as photons. The photons are basically particles of light that carry energy, and that's basically what we see. The photons actually hit the rods and cones of our eyes to, cause an excitation to get transmitted to your visual cortex, so you can perceive something at that particular wavelength. Um, the light that's emitted from the LED, what do we call it? That's a fantastic question. We call it monochromatic light. So basically, it's one color. The LED, the light that comes from an LED is usually monochromatic, and so it's either going to be like red, green, or blue. Even the LEDs that can do all the colors, right? Depending on which leads you hook up, it's either going to do those or it'll do some kind of combination that you'll perceive as a different color. So this is because that energy being released by the electrons is very specific, and it determines those three individual colors of light. So just a quick biology thing here. When we talk about how many different colors of light we can actually see, well, we really can't see anything other than red, green, and blue, or what is it, magenta, cyan, and whatever the other one is. Yeah, so we really only see three colors. Um, and it's a combination of those different colors and the mix of those wavelengths that allow us to see all the different combinations of frequencies that we perceive as other colors. So, do other colors really exist, or is the whole world just made up of these three at a certain combination, and we interpret it that way, right? Interesting. Great question. So, how does an LED work? Right? It allows electrons to move across that special barrier. It releases energy in the form of light when they combine with holes. And then light is made up of photons, particles, and it's usually in one color. Right? So you'll have to ask a physicist who studies this specifically to determine if it releases more than one color. But if it's red, blue, and green, they're so distinct. I mean, I guess you could have an LED that would shoot those three colors out uh, at the same time to give you. No, we do that. What am I saying? We do that. If you ever have those LED strips like at your house, right, and you can change it, it's got a whole list of buttons, and you hit white, you hit red, you hit green, whatever. All of them are a mixture of frequencies that the LED is actually emitting. So you can mix two different colors to get a perceived color. But none of those other colors actually exist. There's some mixture of the three primary colors. Oh, tell me I was recording. Yes. Okay. Jeez. All right. So let's continue with LEDs and talk about its forward biasing. So typically forward biasing for an LED is about 1.2 volts to 3.2 volts, right? Every electronic device requires a certain amount of voltage for it to like push or do work. So for an LED, this push is called the forward voltage. And it's usually between 1.2 to 3.2 volts, depending on the type of LED. And so it just means that the LED needs this much voltage to start lighting up. This is um, higher than what a regular silicon diode needs, which, if you remember, was 0.7 volts to forward bias the diode. The reason LEDs need more voltage, great question, and that's because of how they're made and how they produce light when electricity passes through them. So the material inside the LEDs, and it's often made up of different compounds like gallium arsenide. That just needs more energy to work, and that's why they require more voltage to get that reaction from something like gallium arsenide. Great question. Again, I'm predicting your questions. The reverse bias, well, it's also on the slide. The reverse bias voltage, but I'm predicting your questions. Um, Good question. What is it? Well, there it says on the slide about 3 to 10 volts. What the heck does that mean? So just like how you can't push open a door the wrong way. You could, you'd break it. Diodes again only work when electricity flows in the right direction. So if you try to push electricity the wrong way, we call that reverse voltage. So for LEDs, this reverse voltage limit is between that 3 to 10 volts. So if you go beyond this limit, the LED can actually break down, um, just like a regular LED, and then you'll cause it to physically burn up or break up. So this limit is lower than the regular diodes reverse voltages, the ones we talked about, the rectifier type diodes. Those can handle much higher voltage before they start breaking down. LEDs can work at higher forward voltages to produce light. They're a bit more sensitive to reverse voltages. You see these in 7-segment displays. These are just LEDs that are arranged in a pattern to give you that 7-segment display. So each one of those little segments is an LED, and they're just arranged to make up alphanumeric characters. Right? So these are the type of displays that you'll see. I don't even know if you'll see them in alarm clocks anymore. Think of old liquid crystal displays, or ones that actually had physical diodes, but they're like they're like little bars. You know what a little 7-segment display looks like, right? Think of an 8 with all the little bars. All right. Oh shoot, can you see me? All right. I'm getting away from the camera. Hopefully I was centered in the camera. Anyway, yeah, 7-segment LEDs and what else? Infrared LEDs. Okay, so IR LEDs. Uh, these are used with IR LEDs. Infrared is just a light that we can't see with the visible eye. With the visible eye. With It's just light that we can't see in the visible range of light. So IR LEDs have both like a transmitter and receiver. So the LED, the infrared LED, another kind of special LED, they don't give off visible light, but they do give off infrared light. And again, we can't see it, but other receivers like infrared receivers can. So your TV remote, for example, has a little IR LED, and it'll send the signal in light, but in light that you can't see. So when you press a button on a remote, the IR sends this invisible light to your TV, and this transmitter, like your remote control, right, sends that signal, gets picked up by a sensor on the TV that picks up that infrared signal, and then it converts it to some function or control or some information that you're trying to uh, relay to the TV. Your garage door openers also have infrared sensors. You have those safety sensors as well. No, those are, you can see those visible lights. I was thinking of the safety lights that go in the bottom, but they do also use infrared LEDs, transmitters, and receivers. All right, but it's just light that you can't see. And I am recording, thank goodness. The next one is a photodiode, right? So you might think that sounds familiar or similar to an LED. Nah, different things. So a photodiode operates in reverse bias. And so it works when electricity, again, is going in the wrong way compared to a rectifier diode. And even though, again, electricity doesn't like to flow, like usual, the diode can still work by detecting light. That's how it works. So you have this small transparent window. It's a tiny clear window. It allows light to pass through, and when light hits the special part inside that photodiode, the PN junction specifically, this is where the reaction happens. So light strikes the area, it helps create this small electrical signal or this little reaction, and then that's what causes the change in that depletion region. When it's reverse bias, when you have reverse bias current in this type of photodiode, the diode um, is um, how does this? So when the diode is in reverse bias, right, you get a small amount of current, just like you do the other diodes, and it creates something called the electron hole pairs. We're still dealing with the electron and the holes um, uh, pairing and then not pairing and releasing energy. And so you got these tiny charged particles that pop up inside the diode when it sort of heats up, when it gets hit with the light, when it gets hit with a reaction. So it heats up a little bit, it pops up some charge. The particles, they come from that depletion region because that's where it's striking. That area inside the diode that helps kind of control that flow of electricity. And so that's kind of how they work. Light physically hits this film. The film's really there just to kind of protect the physical uh, component inside. Uh, so it's transparent to allow light to go through and not much else. And that's it. Light goes through, photons go pass through the transparent membrane, hit the diode depletion region. It creates a little bit of energy and heat is energy as well. And so it just gives it enough energy to cause those electron hole pairs to get excited and move. And then we detect those. So that's not too much. That's good. All right. So let's look at this slide. I like this visual. So when the PN junction is exposed to light, right, the reverse current increases with the intensity. So light shines on it, something special happens. The more light, I was going to make a joke. The more the more light that hits the photodiode, the more electric current it produces. Even though the current is flowing the wrong way, called that reverse current. So the brighter the light, the stronger the reverse current. I was going to say something magic happens in the air, and holes and electrons pair. Oh, that rhymes. Okay, I'll try it next time. But what about when there's no light, right? The reverse current becomes negligible. We call this dark current. So when there's no light hitting the photodiode, the reverse current is almost nothing. Like it's never nothing. But you do have a small bit of nothing, and that small amount of current is called dark current. We call it dark current. Um, and we call that because this is what happens when you have no light, right? You're not getting anything, but something is still happening. So the photodiode basically is just waiting for light to start hitting it again so it can start working properly. And that's it. Other than that, current is almost zero, and we say it's in like a sleep mode. But we know that practically some current is always leaking, right? Nothing is ever shut or completely open or completely shut. That's it for this first lecture. Thank you very much. It took me a lot longer, 38 minutes, but I will see you in the next lecture.